Hi everyone, my name's Louisa and I'm a student at MIT, and today I'm going to be teaching you about a microscopic view of how current moves through a wire, especially about why the idea of electricity flowing or electrons flowing is a little bit flawed. The typical model taught to high schoolers and other people studying introductory physics is that electrons sort of move through a pipe, and the wire just acts sort of as a pipe that they can move through. So in this drawing, I'm doing that. I'm following the basic model that's often taught, which is wrong. These little blue dots represent electrons, and supposedly they're just floating through, and that's how we get our current. Now, this doesn't really make sense, because you know that the metal in a wire isn't just made of electrons, and it's also not really hollow. So the way that electricity actually moves through a wire is a little bit different, and let me show you how that actually happens. You may have heard that most wires used for conducting are made of metal because metal is a good conductor, but you might not know why, on an atomic level, metals make the best conductors. The reason for it is actually because they have an outer level of electrons that are loosely held, and that means that they're able to break free of the nucleus's pull and then travel along the wire. Copper is an example of a metal that is commonly used in conductive wires, so let me show you what a copper atom looks like. This is an image of a copper atom that I found on chemistry.about.com, and as you can see, the outer level of electrons has only one electron in it. That makes copper a very good conductor because that electron is not held very tightly by the nucleus, because if that electron is released, then copper would have a full valence shell, and that's very favorable. That's a very stable configuration for the electrons. So essentially what you need to know is that metals have very few electrons in their outermost level of electrons, and those can easily be released, and then they can travel through the metal in a way that I'm going to explain right now. Now here I've just drawn three very simplified versions of copper atoms, and you'll see that I've only drawn the outer electron, since that's the one that we're most interested in. Now, when there's no current flowing through a wire, that doesn't mean that no electrons are moving. It means that there's no net movement of electrons. So in that case, we're going to see that these electrons, since they're not held very tightly, are still going to move around. But they're going to move around in random directions. So this one might go this way, and this one might go that way, and that one might go this way, and then there would be many, many more atoms, and they all would have that one loose electron which would just drift. And that electron is going to move between atoms. So, if this were an actual wire, we'd have another copper here that's going to accept this electron, one would accept this electron, and there would be one over here to accept this electron. So the basic idea is that the electrons move from atom to atom in a metal because none of the outer electrons are held very tightly to the metal. This forms what's known as an electron gas because those outer electrons can move fairly freely and fairly randomly between atoms. Now, like I said, when there's no net electric field, they're not going to all move in one direction. In fact, there's going to be no dominant direction for them to move in. So there's going to be no net current. Now let's take a look at what happens when there is an electric field, and that's when we're going to start to see a real current appear. So here we have a microscopic view of some copper metal, and we're going to apply an electric field to it and see what happens when a current is actually traveling. So this is going to be the direction of my current. That's also the direction of my electric field. Now, here's something that's a little bit tricky that you need to keep in your mind. Since electrons are negatively charged, they actually move in the direction opposite the conventional current and also in the direction opposite of the direction of the field. So since our current is moving to the left and our field is directed to the left, our electrons are going to have a net motion of moving to the right. Now, it's important to know that they're not all going to go straight to the right. That's a little bit too simplistic. They're going to move right in their net motion because due to the electric field, more of them are going to be moving right than are moving left. So let me give you an example of what we might see happening in a sort of a weak electric field. This electron, it might go to the left a little bit because not all of them are going to be forced to go directly to the right. This one might go to the right. This one might go to the right. This one might go a little bit to the left. This one could go to the right and down. And this one could be going straight up. The direction is still fairly random, but you'll notice that if you were to sort of summarize all of this motion, they're mostly going to the right. So that would have a net motion of electrons to the right, and therefore a net current moving to the left. Because again, the direction of the movement of electrons is opposite the direction of the conventional current. So as you can see, the movement of electrons in a wire is not simply free electrons floating through empty space. It's more a series of jumps as an electron jumps from atom to atom, and the net motion is opposite the direction of the conventional current.